Okay, this is 9.3 homework help. First problem says determine the size of the sample space that corresponds to the experiment of tossing a coin a certain number of times. So 3 times. You can start writing this all out, write the whole sample space out if you want. I mean, there's not that many here. You know, you can get true, 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 false, true, false, true, and so on. You keep doing this. You're going to find there's 8 total possibilities. I like to look at this as a tree diagram. So your first toss, you could get either true or false. Second toss, you could get either true or false. Third toss, you could get either true or false. So if you were to write this whole thing out, you know, and do this side as well, you have 4 on this branch, 4 on this branch, there'd be 8 total. Or you can just multiply the branches. You have 2 possibilities. So you have true or false for the first toss times true or false for the second toss, and then 2 for the third as well. So it's 2 times 2 times 2, which is 8, or 2 to the third. So for 5, it'd be the same thing. It'd be 2 to the fifth, which is 32. And you can follow that pattern. It'd be 2 to the n for the last one. So for the next problem, if the probability that an event happens is 1 to 9, then the probability for E would be 1 to 8, and the probability against E would be 8 to 1. I guess and to try to explain this, there's one event that we're looking for that we would say 1 here, and then there must be 8 other than in the sample space total, because there's 9 total in the sample space. There's 8 other things in the sample space that don't count. So say we're looking for 1 red marble out of a total of 9. That means there's 8 other marbles that aren't red. So that's why you would do 8. Okay, the next problem says the sample space contains 7 sample points. I made the diagram a little bigger here in this Venn diagram, and it gives us the probability of each of the individual events located throughout here. And it wants the probability of A or B. So what this means is A union B means all the events, because it's either the events that happen in A, which is all these events, plus, or it could be any of the events that happen in B, which is all of them. And we know that the sample space has to add up to 1 always. So the probability that we select something randomly out of here, obviously if we choose everything, that's got to be 1. So then the probability of A and B is the intersection. So we're just talking about the probability of 2 and 3 added together. 2 and 3 both have a probability of 0.05, so that'd be 0.1 if you add them together. And we can skip these two. I'm not going to ask you anything like that. I'm not even sure what they want here. Okay, the next problem says in an experiment, a fair coin is tossed 14 times, and we can get head or tails. How many elements in the sample space will have no tails? Well, that's only 1. All heads. There's only one way that can happen. If you look at this as a tree diagram, you have heads, tails for each of these choices. And you could write out the whole sample space if you wanted to write out 14 of these, which would be a really big tree diagram. But we'll just answer the first 2 questions here. How many elements of the sample space has exactly 1 tail? There's 14 different ways you could do that. You know, you could choose the 1 tail this way, and then you got to go heads the rest of the way out, or you could go head and then choose your 1 tail here and go heads the rest of the way out. But there ends up being 14 ways you can do that. And we're not going to worry about the last 2 questions. I'm not going to ask you anything like that. Okay, the next problem says in an experiment we're going to a ball is drawn from, I think it's a typo, from a bag or something containing 13 purple balls and 9 orange balls. If a ball is purple, 2 coins are tossed, and if a ball is orange, 3 coins are tossed. So we first have a choice between purple and orange, and then if we get purple, we could have heads or tails. So if we multiply the branches of this, there's 13 ways we can get a purple. There's 2 here and 2 here. So if you multiply those together, you get 52. That's the sample space for the purple ball. And then the sample space altogether would be this 52 plus this orange down here, which is now you've got heads, tails for each one of these. So you'd have to do 9 times 2 times 2 times 2. So you'd have to add this with this, and total that would be 124 for the total elements in the sample space. Okay, the next problem here I'm going to have to make extra credit because I'm trying to figure it out and I can't. And there might be a few problems like this in this assignment because this is just not Not my strength. I won't ask you a question like this on a test, obviously. But if you guys can figure this out, that'd be fantastic. I tried to do this 2 different ways using the information they gave me. I tried to make a tree diagram here, married and unmarried. 59% of people are married, which means 41% are unmarried. Of the people that are married, 24% are college graduates. That means 76% of the people that are married are not college graduates. So that gave me, if you multiply the branches of this, you get 14.16% of the people are married and college graduates, which also comes from this conditional probability formula on our formula sheet, because if you say A is a group of people that are married, B is the college graduates, then the probability that someone's a college graduate, given that they're married, they gave us in the problem is 0.24. And they also gave us the probability that someone's married, which would be A, as 0.59. So you can multiply both sides and get the probability that someone is married and college graduate, which is 0.1416. But so I was also able to get the probability that someone's married and not a college graduate. Should be 0.4484, but that didn't seem to work when I tried that. So I'm missing something here. I'm not sure what it is. 1/3 of college graduates are married is something I didn't use, and I don't know how to use that. So I guess for now, let's just move on. Okay, the next problem says, it gives us this table here. It says a person is randomly selected. What's probably the person is male? Well, male, we just find the total, 141 over 278. Next question wants us to find the male and a Democrat. Male and a Democrat, that's 27 out of the total 278. And then the next question is a hard one. It says, what's probably someone's male given the person's a Democrat? So that's male given they're Democrat written like this, which if you compare it to our conditional probability formula, because that's what this is, the condition is that they're a Democrat. You can just follow this and say, okay, well, we need to find the probability that they're male and Democrat, which we had already found. That was 27 out of 278. We also need to find the probability of A, which is that the probability that they're a Democrat. Now, the probability someone's a Democrat is 91 out of 278, so I put that in the bottom. Now I can use that formula to find this. Just divide these two numbers, and that gave me 0.2967 about. So for the next one, find the probability that someone's Republican given that they're male. So I'm going to write Republican given that they're male, and then just fill out this formula. So I need to find the probability that someone is Republican and male divided by the probability that someone is male. So we have the probability that someone is male. That's this number in the bottom would be 141 over 278. So we need to find the probability that someone's Republican and male. So Republican and male is 87 out of the total 278. And if I divide those two numbers, I get 0.617. Okay, the next part, find the probability is someone's female given that the person is independent. So if you follow this conditional probability formula, just fill it out. Probability someone's female given that they're independent is the probability that they're female and independent divided by the probability that someone's just independent. So the probability someone's female and independent would be 12 out of the total 278. And the probability that someone is independent would be 39 out of 278. So if I divide those two numbers, I get 0.308. And the last question is no, they're not independent. The conditional probability formula wouldn't have worked if they were independent. Okay, the next question says we're going to draw a single card from a deck of 52. We want the probability that it's a face card or a number card. Face cards, there's 36 face cards in the deck. There's 2 through 10 with 4 each. And then 16 of ace, jack, queen, and kings. There's 4 each of those. So it's 36 of 52 plus 16 of 52, which is the total sample space. So that's just going to be 1. So when events are mutually exclusive, you can just add them. So the probability of A or B, when it's mutually exclusive, it's the probability of A plus the probability of B. So mutually exclusive, you might want to write this down. And then if it's not mutually exclusive, the events, then it's the probability of A or B is going to be the probability of event A plus the probability of event B minus the overlap. The overlap would be A and B. And that comes right from picturing a Venn diagram. If there's overlap, then the probability of A and B, you got to subtract the overlap in the middle to get the OR, which would be this whole thing in the middle here. So this should make sense if you just look at a Venn diagram of the two events. And if you think about it, so the probability that's a queen and a 3, well, there is no queens that are also 3, so that's 0. The probability that it's black or a 3, so now these are not mutually exclusive because some blacks are 3, so we're going to have to use this. The probability that it's black would be 50% because that's half the deck. Plus the probability that it's a 3, there's 4 out of the total 52 that are 3s. And then I have to subtract the ones that are the same, and there are 2 cards in the deck that are black 3s. So the 3 of spades and the 3 of clubs. So that'd be subtracting 2 out of 52. So you'd have to do this, which gives you 0.5385 or about 53.9%. But it's picky about decimal places here, so enter in 4. All right, next we want black and a queen. Once again, not mutually exclusive because there are 2 queens that are black. So probability you have a black card would be 50% plus probability you get a queen. I'm sorry, black and a queen. That's not or, that's and. So for and, you want to think about the ones that are black and also queens. They're just 2 out of the total deck of 52. So that'd be 2 out of 52. You can enter in just like that. All right, and the last one, probably that's black and a face card. We talked about there being 16 face cards, so there must be half of them are black, half of them are red. So it'd be 8 out of 52. And you can just enter it in just like that. Okay, the next problem I've written on all the formulas. These are the conditional probability formulas written both ways for E given F and F given E. Just plug in for A and B basically in the formula sheet. And then this is the formula for dependent events, which these are. So we can say no here. You almost want to answer this question first because if the answer were yes for this one, then this would go away. Because mutually exclusive events, you just add the probabilities together. So since we know that the answer to this is no, now we can go ahead and answer these really easily based on what they gave us here. So if we're looking for the probability of E, that's right here. To solve for that, we would just plug in what they gave us here, which is 0.2975, and what they gave us here for probability of F given E, which is 0.7. If you solve for P of E, then you get 0.425. Now you can do the same thing for probability of F. That's the variable right here. Once again, we have this value is 0.2975, and we have this value, probability of E given F, they gave us just 0.35. So just cross multiply, solve, and you get 0.85. Now the probability of E or F is this formula right here. So we're going to use these two probabilities, 0.425 plus 0.85 and minus the intersection of the two, which is 0.2975. And that gives us our answer for that of 0.9775.